Welcome back to another Rise Explainer video. This video is about modeling manufacturing resources using the ISA-95 standard. I argue that if you learn these fundamentals, you'll be able to model the resources needed for virtually any manufacturing process in the world, no matter its size, scope, and scale. ISA-95 has 4 resource models. The names probably provide a good hint of what they do. Equipment is what the firm uses to make things. Material is what is consumed or produced in the process. Personnel are the people who operate the equipment and handle the material. And physical assets are a bit more niche, so I'll just touch on those at the end. In short, they are for use cases where you need to track information about an asset that can be swapped in and out of equipment roles. Our focus is on ISA-95 as a data model. A data model is going to have entities, relationships, and cardinality. Entities are the objects in our data model. An oven might be an entity. Other examples of entities are the max temp and current temp properties. Relationships are the connections between entities. In this case, the relationship is that the oven has these properties as a part of its composition. Cardinality is the number of entities that can exist at each end of the relationship. Here, our oven has 2 properties, but each of these properties can be related to only one equipment entity. In this case, we say the cardinality of equipment to equipment properties is 1 to many. All resource models have entities for classes, instances, and properties. Instances are the physical thing, like an oven. Properties are temporary or permanent characteristics of this thing. Instances are defined by classes. From the other side, classes group and configure instances. Your classes can have class properties that they pass to the instances they define. If an instance belongs to a class, it inherits the properties. The property values for the entity map to the class property. This structural symmetry holds for all these models. So if you learn to apply the pattern for one model, you can apply it for others. This all makes more sense with some examples. Let's run through how these relationships look in practice. Let's start with equipment. Equipment classes can define multiple equipment items. For example, my oven's class defines the 2 physical ovens in my kitchen, oven 1 and oven 2. This class has properties for state and current temp, and my oven instances inherit these properties. But these properties also have values, which may differ. For instance, oven 1's state property is off, and its current temp is 25 degrees. Oven 2's state is on, and its current temp is 250 degrees. These equipment property values map to their associated class property. Equipment can also be a member of multiple classes. For example, imagine a plant makes multiple products, and each product is made with a different degree of automation. It might have a packing class with an infeed property that applies to all packing centers. It also might have a camera-assisted class for jobs that use machine vision to inspect, measure, and what have you. This class has a property for the pixels of the camera. In this plant, there's also a robo-filler that bottles beverages and then uses a camera to check the bottle. In this case, the robo-filler is a member of both classes and has values for the properties it inherited from each one. The material model follows the same principle, but it has an extra layer of abstraction, and I'll explain why. Imagine I manufacture various computers and computer parts. I might build a class, CPUs, to create a template for all CPU properties, number cores and clock speed, and so on. Let's say that my operation involves one of 2 CPU brands, the Cool Tortoise and the High Temp Hare. Each of these inherit the properties of its class. However, unlike the equipment model, these class members do not correspond to physical things in production. Unless my business is a complete disaster, I'll make or use a lot more than 2 CPUs. Rather, these CPU brands are material definitions, and each instance of this definition is a material lot. Here you can see the multiple lot IDs that correspond to my material definition. These chips are the instances of my Cool Tortoise CPU brand. The relationship between material definitions and material lot is one to many. Entities also can have relationships to entities of the same type. All classes can include properties from other classes. For example, the GPU and CPU classes may both include properties from the processing unit's class. Returning to equipment, a silos class may be a member of a vessels class and inherit its volume property. Another relationship that happens between entities of the same type is the made up of relationship. Equipment can be made up of other equipment. For example, this kitchen center is made up of the equipment oven 3 and the mixer 34. You can define this relationship on the class level too. For example, you might define a packing center as being an equipment class that is made up of bottlers, cappers, casers, and palletizers. The corresponding material relationship is the is assembled from relationship. For example, an instance of the packing center that we just described might produce bottles of juice, which are packed into cases, which are packed into pallets. The pallet is assembled from the case, which is assembled from the bottle. I haven't yet touched on personnel. That's because it's almost identical to the equipment model. A personnel class, such as operators, can define multiple persons. A person who is defined by the class inherits the class's properties. In this case, operator 1 inherits the hire date property. A person can also be defined by multiple classes. This person is the lead of the pharma quality team. They inherit the properties from both the chemists and quality classes. A personnel class can even have an is made up of relationship. For example, this packing operators class is made up of packers and stackers. There is one difference in the entity relationships between equipment and personnel. Equipment instances can be made up of equipment instances, but persons cannot be made up of other persons. That is physically impossible. Lastly, as I mentioned, the standard also has a physical asset model to track info about swappable equipment. For example, imagine that my plant has multiple spare robofillers. Periodically, these robofillers are rotated in and out of a particular bottling process. In ISA-95, equipment has a role in production. An equipment ID is about a role, not the serial number of its underlying object. However, it might be necessary to record info about that asset that performs the role. For this use case, use the physical assets. In this relationship, we can say that the equipment is implemented by whatever physical asset fills its role. Now, your data can include histories about both the equipment and the asset. So, those are the fundamental resources in ISA-95. They apply to all phases of manufacturing. If you want to go farther, you could look into how to specify resources to be used and consumed as a part of process definition. Or use the resource capabilities along with the process definition to plan how many products you can manufacture. Or your MES might use the resource model to actually execute job orders. Or when that's done, these resource models provide flexible data objects to analyze and track performance from different perspectives. Thanks for watching.